All right, let's jump right in. How do you join two things together that, well, fundamentally refuse to be joined? Today, we're looking at a huge engineering puzzle and the incredibly clever laser-sharp solution that researchers came up with.
So it all starts with something we can all get behind, building more fuel-efficient cars. And really, the best way to do that is to make them lighter. This has kicked off a massive search by automakers for new materials that are both super strong and super light.
And two materials have really come out on top. First, you've got this stuff called ultra-high-strength steel. It is unbelievably strong, which is exactly what you want for the safety frame of a car. And then you have super lightweight aluminum alloy, which is just perfect for things like doors and hoods. They are the absolute dream team for building a light and safe car.
So what's the catch? Well, you can't just weld them together. They are so different on a physical level that if you try to weld them, you get this really brittle, weak connection that's frankly completely useless. This has been a massive roadblock for engineers for a while now. How do you get these two perfect materials to actually play nice together?
Okay, so welding is off the table. Engineers then turn to mechanical methods, and the usual go-to technique is something called self-piercing riveting. But, they hit another wall pretty fast. The very thing that makes this new steel so awesome, its incredible strength, was also the very thing that made it impossible to join.
So what exactly is self-piercing riveting, or SPR? Just think of it like a giant, super-powered industrial staple gun. A machine uses a ton of force to punch a special rivet right through the top layer of metal. It then flares out and locks into the bottom layer, creating a super strong bond. No heat, no drilling, just pure mechanical force.
And this is where things get really wild. On the one hand, you see the process working perfectly. That's SPR joining older, weaker steel. It's a clean, solid connection. But then, you see what happens when that same rivet goes up against this new 2.0 gigapascal steel. It's a catastrophe. The steel doesn't bend, it doesn't budge, it literally shatters the rivet into pieces.
So, the takeaway here is pretty simple. The old methods just failed because the new material was, it was too good. It was just too strong. It was like trying to hammer a nail through a diamond. Brute force was clearly not the answer. They had to think differently.
And that new approach came from a brilliantly counterintuitive idea. Instead of trying to use even more force to overpower the steel, what if you could just, convince it to cooperate? What if you could tame it, even just for a split second, with nothing more than a beam of light? And this is the result, the laser-assisted process. It's this elegant two-step dance. First, a low-power laser draws a tiny circle right where the rivet needs to go. Now, it doesn't melt the steel, it just heats it up enough to create this temporary, perfectly targeted soft spot. And then, the standard riveting machine comes in and just punches the rivet through that softened area like it's no big deal. Of course, having the idea is one thing, but making it actually work is a whole different ballgame. The researchers had to find the absolute perfect settings, the right laser power, the right number of passes, to get it just right. Too little heat, and the steel stays too hard. Too much, and you create a whole new set of problems. They had to find what they called the Goldilocks zone.
And this is basically the map of their entire journey. Every colored block here represents a different experiment with different settings. And as you can see, most of it is failure, cracks, bad connections, you name it. But see that little green window right in the middle? That's the zone. That's proper joining. That's Goldilocks.
So how did they know they were hitting that sweet spot? Well, they measured the hardness. I love this analogy. Think of the steel's original hardness as a giant mountain. The laser's job wasn't to blow up the mountain, but to carve a perfect little valley of softness right through the middle. That way the rivet could just pass right through without a fight. And just look at how well they nailed it. The original steel had a hardness of 666 on the Vickers scale. That's just a standard way to measure how tough a material is. Now their target for a successful joint was to get that number below 420. And in that Goldilocks zone, they got it all the way down to 347. They didn't just hit their goal, they absolutely smashed it.
Okay, so they've successfully softened the steel. Check. But how do you really know if you have a good joint? What's the one single measurement that tells you if this thing is actually going to hold up?
It all came down to this one number, 0.2 millimeters. That's the magic minimum for what's called the interlock width. So the interlock is basically how much the rivet flares out underneath the steel to lock itself into the aluminum. If that flare is less than 0.2 millimeters, the joint is weak. But if it's more, you've got a solid, reliable connection. This became their ultimate measure of success.
So, let's bring this back to the real world. What does all of this mean? Because this isn't just some cool lab experiment, it's a genuine breakthrough that could change how we build the next generation of cars.
And the result? Well, it's pretty much perfect. You're looking at a cross-section of the final joint. It's clean, it's flawless, and it is incredibly strong. This is really the victory shot. It's a bond made possible not by brute force, but by pure precision. And here's the winning recipe. A pretty low laser power of just 200 watts, making 3 quick passes. And the final result? A joint that can handle over 8 kilonewtons of force. To put that in perspective, that's like hanging a whole car from just one of these tiny rivets. It is a seriously, seriously strong connection.
So what's the big takeaway here? This process finally cracks the code on joining this super strong steel to aluminum. It makes an incredibly strong bond, and maybe the best part is that it uses way less energy than other methods. It's smarter, it's more efficient, and it gives car designers way more flexibility.
And that really leaves us with a final thought to chew on. This team solved a huge problem using about a fifth of the laser power that some other attempts had used. They didn't just throw more power at it, they added more intelligence. And it just makes you wonder, right? What other huge problems are we trying to solve with brute force when the real answer might just be a little more precision?